In the next few videos, we'll study the behaviour of Markov chains. Let's start with a couple of illustrations. Here's a model we've looked at before, a model for the spread of an epidemic. I'm showing 5 different simulations here, all with the same parameters, d equals 14, r equals 1.1. I've started them all at x0 equals 5. In some of the simulations, the epidemic dies out completely. It ends up in state xn equals 0, and it stays there. In other simulations, it switches into an almost perfectly deterministic exponential growth curve. Same parameters, it's purely down to chance which happens. But that's not the only sort of behaviour we might see when we simulate a Markov chain. There are some models that would expect to settle down to an equilibrium behaviour. If we wanted to model an endemic disease, for example, rather than a pandemic, we know it's never going to die away completely because there'll always be new seed cases, and we also know that exponential growth can't continue forever because we'll run out of people to infect. So it should end up in some sort of natural equilibrium. In this video, I won't go into a model for an endemic disease, that's left for the example sheet, but instead I'll introduce a different Markov model that does settle down to an equilibrium. I'm calling this an active users model. Think of it as a model for the number of users currently using an online platform, for example. In each time step, each user might depart, just the same binomial term as we use for the epidemic model. The difference is the new users term, which I'm modelling here as a simple Poisson random variable with the fixed parameter lambda. The average number of new users each time step is constant, whereas in the epidemic model, the average number of new infections was proportional to the number of current infected. And this turns out to make a massive difference. Here are 2 simulation runs of the active users model. I'm also plotting a histogram showing the long-run fraction of time spent in each state. 2 histograms, one for each of my 2 simulations. The number of active users hovers around 17, and the longer we run the simulation, the more regular this histogram is. The next few videos will all be about how we figure out what sort of behaviour a Markov chain has. These are the sorts of questions we'd like to be able to answer about the epidemic model. How likely is it to die out? And if it doesn't die out, then what's the growth rate? And how do these answers depend on the parameters? For the active users model, what's the average number of active users? And what's the distribution of that number? In other words, what's the shape of the histogram that the Markov chain settles down to? The next 3 videos will give tools to answer all of these questions.